So all synovial joints consist of the same fluid-filled capsule structure, but they do differ due to the shapes of the articulating surfaces of the bones that are found within those synovial joint capsules. So here we're going to take a look at 6 types of synovial joints. We're going to see plane joints, hinge joints, pivot, condylar, saddle, and ball and socket joints. And we're going to look at some specific examples of these along the way. So let's start with the plane joints. So at plane joints, the articulating surfaces of the bones that come together within that joint are flattened or only slightly curved. So what this allows the two bones to do is that the two bones within that joint can slide or glide over one another. Now this motion is usually constrained because of the fact that at these joints there tend to be numerous ligaments that are found outside of those synovial joints. So those many ligaments tend to restrict the movement of these plane joints. So due to their gliding nature and the fact that there are a number of ligaments external to the synovial joints that constrain their motion, these are classified as non-axial movements. Some examples of some plane joints are the joints between the carpal bones, so we call these the intercarpal joints. The joints between the tarsal bones, we call these the intertarsal joints. And also the joints between the articular surfaces of the vertebrae. So next up we have the hinge joints. So at hinge joints, there is a convex cylinder-shaped end of one bone that articulates or fits pretty snugly within the concave kind of trough end of another bone. So this configuration approximates a hinge-like structure, like a hinge we would see on a door. This type of joints permits angular movement along a single axis. So therefore, these are classified as uniaxial synovial joints. So the elbow joint between the humerus and the ulna is a really excellent example of a hinge joint, as are the knee joints, so that is the joint between the femur and the tibia, as well as the joints between the phalanges, which are called the interphalangeal joints. So these are all capable of uniaxial hinge-like motion. So moving on, we have pivot joints, which is another example of a uniaxial synovial joint. So at pivot joints, we see that there is a rounded portion of a bone that is enclosed within a ring-shaped structure that is formed partially by the articulation with the second bone at this particular joint and partially by a ligament that surrounds the rounded portion of the first bone. So the rounded portion of that first bone is then capable of rotating or pivoting that bone about its long axis. So because this rotation occurs around a single plane, that makes these types of joints uniaxial synovial joints. So a good example of this is the joint between the proximal radius and the proximal ulna, which allows the radius to rotate over the ulna during that pronation movement of the forearm. Another example is the joint between the first cervical vertebra, which is called the atlas, and the second cervical vertebra, which is called the axis. And this allows the atlas to pivot about the axis, which allows us to laterally rotate our head from side to side, like when we're shaking our head no. So those are some examples of pivot joints in the body. We'll next take a look at the condylar or the condyloid joint, which is the first of our biaxial synovial joints. In this joint, one bone at the joint has a rounded surface, while the other bone has a small, shallow depression, and so these two ends kind of fit into one another and form the condylar joint. An example of a condylar joint are the knuckle joints between the metacarpals and the proximal phalanx of each finger. So this is a good representative condylar joint. It allows the knuckle to move in two planes. So if you fan your fingers apart, that demonstrates movement at the knuckle joint in one plane. And then if you flex and extend your fingers toward and away from your palm, that represents the second plane of motion at the knuckle joint. So we have a good example of our two planes of movement at our condylar joint there. So the saddle joint is a joint that has biaxial and multi-axial examples. So the joint itself consists of a saddle-shaped bone that that would be the shape of the first bone at this particular joint. The second bone at the joint has a shape that resembles the legs of someone sitting in that saddle. So this allows the bones to fit together like a rider sitting on a saddle. An example of a biaxial saddle joint is the joint between the trapezium, which is a carpal bone, and the first metacarpal, which is found at the base of the phalanges that belong to the thumb. So this joint permits opposition of the thumb as well as the abduction and adduction of the thumb, so that represents movement at the thumb in two planes of motion. So this is a biaxial example of a saddle joint. We also have multi-axial examples of synovial joints, of saddle joints rather, in the body. The sternoclavicular joint, where the manubrium of the sternum meets the clavicle, is a saddle joint, and it is a multi-axial or triaxial synovial joint. So at this joint, the clavicle is capable of moving superiorly and inferiorly, so that's the first plane, anteriorly and posteriorly, which is the second plane, and medially and laterally, which is the third plane. So this is a multi-axial or triaxial example of a saddle joint. And finally, the ball and socket joint in the body are all capable of multi-axial movement or triaxial movement. Whichever term you prefer there is perfectly fine with me. There are two ball and socket joints in the human body. The first is the glenohumeral joint at the shoulder. This is where the humerus meets the glenoid cavity of the scapula. The second is at the coxal or the hip joint. This is where the head of the femur fits into that deep socket called the acetabulum on the hip bones. So the proximal end of the humerus and the proximal end of the femur all have this kind of spherical shaped piece of bone which fits into the socket on the scapula or the hip bones respectively there. So we turn our attention to the shoulder for a second. We see that the hip bones rather. We see that the acetabulum on the hip bone is a very deep socket, and it very tightly secures the head of the femur within it. So this is really important for stability of the hip joint because the hip has to transmit the weight of the body to the lower limbs. So because of that, it is much less mobile than the shoulder joint is, because we have to have that trade-off, we have to have that sacrifice between mobility and stability. So we have to sacrifice some of that mobility at the hip joint for greater stability. And indeed, we do see that the hip joint is much less mobile than the shoulder joint, even though they're the same type of joint. They're ball and socket joints, right? Turning our attention real briefly to the shoulder joint, we see that the shoulder joint is capable of a much greater range of motion because the socket that's made by the glenoid cavity on the scapula is very shallow. Since the shoulder is not a weight-bearing joint, some of that stability at the shoulder joint can be sacrificed for much greater mobility.